This video is part of the lecture for multivariable calculus, and I'm going to talk about extreme value theorem and how to find a global maximum or minimum of a function of two variables. So let me start. The theorem says this. This is extreme value theorem says that let f be a continuous function on a subset of R2, okay, and assume that D is closed. Okay. What do I mean by saying that D is closed? I mean this, that D contains all its boundary points, its boundary points. For example, we might get x squared plus y squared less than or equal to 1. This is the unit disk, and since we have inequality in here, it's inside the unit disk, and also we have the equal sign, and so which means that it covers all the points on this boundary. Then if it is closed and bounded, what do I mean by saying that D is bounded? It means that D is contained in a disk of some radius r centered at the origin. For example, if this is our D, okay, I can just put it, this is the origin of a disk of radius r. That's why we say that D is bounded, and we say that D is closed. It means that D contains all of its boundary points, like this. Okay, so if you have these two conditions on D, and also f is a continuous function, then we say f has global mean, a global minimum, and a global maximum on D. Okay, so D should be closed and bounded, and f, the function f, should be continuous. In that case, for sure, we're going to have a global maximum or global minimum. And now the question is this: how to find global mean or global max of a differentiable function. Since it's differentiable, it's for sure continuous. Function f on the domain D. Okay, the first thing we need to do is to find the critical points. Find the critical points of f in D, okay, and then the values of f at those points. How to find the critical points? We need to say that the gradient of the function f is 0 at the critical points, which means that the partial derivative with respect to x and partial derivative with respect to y are 0, or we can say that the partial derivative with respect to x or partial derivative with respect to y, if just at least one of them does not exist, then that point is also a critical point. And the second condition is that we need to find extreme values of f on the boundaries of D. Find extreme values of f on the boundary of the domain D and also at infinity. So we check the boundaries of D and then we plug in the boundaries into the function, and then we look at the maximum or minimum value of the function f on the boundary, and also we need to check at the infinity. Then if we have all of these points, critical points, and the boundary points, then the largest of all values of f, okay, at the extreme values on the boundary and also the critical point, gives the global maximum, and the smallest of all the values of f at those points gives the global minimum. Okay, that's how we find the global mean or max. Okay, and let me give you a small note, is that based on the extreme value theorem, if D is closed and bounded, then for sure max and mean are attained. Okay, otherwise they may not exist at the points. Let's look at one example. I'm gonna look at the function fxy equals to x. Okay, and at, let's say D is x squared plus y squared less than 1. It's the open unit disk. Okay, we can check and find the critical points of f, but if we look at this is the equation of a plane, so it doesn't have any critical points, and because the partial derivative with respect to x, so if you look at that, let me write this. The partial derivative with respect to x is 1, which is not 0, and the partial derivative with respect to y is 0, so we cannot find a point that satisfies both equations that are equal to 0, so it doesn't have any critical point, and also partial derivatives that exist, so there is no critical points. Now let's look at the boundary of that. The boundary of D is boundary of D. The boundary of D is just the unit circle, because I have this shape. This is x-axis, y-axis, and then basically, actually let me graph it like this. It's the unit disk, but in this open unit disk, since the boundary is not included, we don't have the maximum or minimum value for the function f. So the biggest value of f equals to x is 1 on this open unit disk, but it is not in the domain. Okay, and also we can say that if we choose any number, okay, we can choose any number, like for example, if you choose the 0.099, there is also a bigger value for that, 0.999, and also there is a bigger value for this. Okay, so any point that you choose, you can choose any bigger number than that. That's why the biggest value of f does not attain in this disk, because it's a unit disk. Let's look at the graph of this function. You see, it's the plane z equals to x, and also we have the open disk in here, and this is actually the boundary of that. And as you see, we might have the maximum value and the minimum value, but the problem is that since we consider the open unit disk, the global min or max, they are not attained for this function.